images. And now we would like to ask a question: how can semi-analytical model helps? So semi-analytical model not only can provide a complementary way to study global properties of the jet funnel region, but also it comes with some benefits, such as it provides a very quick way to simulate the environment. And it's usually flexible for fitting in different free parameters. And also it is educational. So it's possible for us to check the components of the semi-analytical models and study how would the results varied. And also for a semi-analytical model includes both horizon scale to large scale properties. It'll be very helpful for us to study from near region to large regions. So the outline would be, we will start with some background knowledge for geometry jet properties. And I would like to share with you some results for a new semi-analytical geometry jet models. These are based on a paper from Pu and Takashi last year. And finally, we would like to apply the jet model to some simulated images. So to start with, let's take a look at the jet accelerator. So consider a hydrodynamic flow. If we accelerate a hydrodynamic flow starting from negligible initial velocity, so with its increasing velocity, it will eventually pass a characteristic point called sonic point and become supersonic. In comparison, if we focus on a MHD flow, so there are more than one characteristic point. There are L1 points indicated in A, and fast and slow magnetosonic points. And if the flow can successfully exceed the fast magnetosonic point, then the flow becomes super fast. And the acceleration of an MHD flow actually is related to the physics converging from electromagnetic energy to kinetic energy. Now, if we include the gravity effects, the whole story vary a little bit. If we include a gravity effect, and if we imagine the flow flowing along some specific field lines, it will experience a magnetocentrifugal force outward and a gravity force inward. So actually, there are outflow and inflow share the same field lines. And for both the outflow and inflow region, there are 3 different characteristic points. And the region where the velocity roughly equals to 0, we call this separation surface or stagnation surface. And for each of the region, we can define a light surface. Beyond the light surface, the flow cannot co-rotate with the field. Otherwise, the toroidal velocity would exceed the speed of light, c here. So as a result, the light surface actually plays a threshold or a reference. Before and after light surface, the flow properties changes significantly. However, what we described so far is a story for one single field line. To model the global properties in the jet funnel, we should include many field lines. And if we decompose the equation of motion, and we can actually project the equation to Chen's field direction and parallel field direction. It is well known, solving the glacial funnel equation, the Chen's field equation perpendicular to individual field lines is a very difficult and time-consuming work. And things can be even more complicated. There are coupling between jet geometry, jet acceleration, and the existence of fast magnetosonic points. So with all these difficulties, so if we ask, is it possible to quickly approximate geometry flow structure in the final regions. And I'm happy to say yes. Now I would like to show you a semi-analytical model. An example result is shown on the top, and we can compare the resulting the GRMHD numerical simulation results. And if we focus on the final regions, the behavior is actually pretty similar. So I would like to very quickly just give you a quick idea about how this can be realized. So let's consider if we start with a force free magnetosphere. So in that case, it's not guaranteed a fast magnetosonic point can exist. However, if we fit some plasmas, so we can take such consideration as a perturbation. With such perturbation, it will modify the original force-free geometry and guarantee the existence of fast magnetosonic points. However, to consider all of this is difficult because we should take into the Chen's field equation. So instead, we can use an approximation. So we can apply some sophisticated constraint for the magnetic pitch angle. So, and force the existence of fast magnetosonic point. And in general, we can do this many times and find a consistent solution. However, it seems even without an iteration, the approximation is pretty good enough. So I would like to show you why and the corresponding results. To have a model overview, the philosophy of the model is the geometry of a highly magnetized flow can still be well approximated by the force-free magnetic field configurations. So the first parameter in our model is the streamline function, which describes the geometry of the magnetic field. And it's parameterized by a parameter P. When P equal to 0, it looks like monopole. P equal to 1, it looks like parabolic. And there are other 3 free parameters. So with all the other 3 parameters, we can single out a unique global GRMHD solution. And the other 3 free parameters, the first one is black hole spin. It must be larger than 0 because we are focusing on the case black hole rotation energy is ejected outward. And the second free parameter is the angular velocity of the field. And in general, it can be a non-constant. So it can vary from streamline to streamline. And finally, that's the energy for the outflow. So after we specify these 4 free parameters, so in this routine, a matching condition is automatically applied, and the model will automatically include the extraction of black hole rotational energy and the.
Oh, sorry, Hangi, just 1 minute about for speaking because we need to give questions. If you would like questions, or unless you don't want questions, then you can keep going for like another couple of minutes.
Oh, thank you. So how much time do I still have?
Like less than 2 minutes.
Less than 2 minutes. Okay. Okay. So I will quickly show some results.
Yeah, I'm writing in the chat when people are running out of time. Go ahead. Yep.
So on the right, here shows some characteristic surface in the final regions. So it's, the model can apply to large scale, and also it can apply for acceleration behaviors with different outflow energy. And the movie shows the spin dependence. No, sorry, the magnetic field configuration dependence. So all these snapshots can be computed in a few seconds. And we can also apply to a parabolic field line, for example, and we can apply constant angular velocity or non-constant. And this is the constant case. So we can see some characteristic surface, and this is non-constant case. And compared to a constant case, near the equatorial plane, it rotates slower. So that's why you can see a V shape near the jet boundary. So we can apply radiative transfer. So I will skip this part and just show some results. So just to give you some ideas. So we will first take a look at the beaming vector on the left. So we will compare the local energy to observer's energy. So the approaching part will become brighter. And on the right is color-coded height. So you can see when inclination angle is low, there are some downward pipe effect. However, the story so far is like an optically seen case. If we consider further, the jet can be optically seen. And here shows an example for jet emission only. And if we further consider accretion, so you can see we really need high dynamical range to observe the jets. So I think I'm running out of time, and I would like to show some results. So here we can also apply the jet to large scale as well. So here are the example for 86 gigahertz, and with different application and considerations. And we can vary Bradford spin or jet opening angle very easily by this semi-analytical approach. So this is my summary, and I'm running out of time, so I will just
thanks a lot. So we can have questions in the chat. So thanks, Hongyi, very much, and Angelo is going to be presenting next. So Angelo's at the CFA, and why don't you take it away, Angelo, if you can share your screen.
Hi, and by the way, I just put a question in Slack, but I should start my own presentation.
Yeah, or Slack. You can use the messages or Slack for the question.
All right, shall I begin?
Yes.
Okay, hi everyone. I'm a postdoc at CFA and the Black Hole Initiative. Today I'll be telling you about probing plasma with spectral index maps. This is a project mostly aimed kind of short-term at ngEHT, although spectral index maps of our sources have not yet been created. But the physics that we probe here will be relevant for ngEHT as well, perhaps even more so when we are able to look at these sources at a much larger dynamic range and image fainter features in the jet, for example. So first of all, what is the spectral index? This is defined as the logarithmic derivative of the flux or the intensity, as we'll see, with respect to frequency. That is, if you have an SED, what is the slope in log space of that spectrum?
Oh, by the way, Angelo, we see your presenter review, so maybe you might want to do it in the.
Oh, sorry about that. I'm just gonna get rid of my extra desktop. That should do it.
Yeah, perfect.
All right. So the point of this is whether or not we can use 230 gigahertz spectral index to distinguish models. What do these maps look like? And is it perhaps just an optical depth map? This is that was our first hypothesis. We're focused here on 230 gigahertz for EHT compatibility. Now, in terms of the observational data for Sagittarius star, we believe that the spectral index is flat and it becomes more negative as you go to higher frequencies. For M87, the situation is actually a bit unclear as far as 230 gigahertz goes for the event horizon scales that we're interested in. There are some measurements at longer wavelengths from the Korean VLBI network that are somewhat confused as well due to differences in the UV coverage as a function of frequency. And then there's also this measurement from ALMA only, but this includes the larger scale emission. So for M87, I would say anything between -1.2 and 0 would be okay until we process event horizon scale resolved spectral index maps. Our methodology is to produce images using IPOL. This is the radiative transfer code that's used in the EHT papers, starting with GRMHD simulations that run to 30,000 M. We looked at both M87 and Sagittarius star. And for this, you of course need several frequencies, at least two. For M87, we looked at 4 of them, 214, 228, 340, and 350 gigahertz for M87. And for Sagittarius star, just 214 and 228. And when I talk about maps in these upcoming slides, I'm actually just going to focus on the 214 to 228 gigahertz range. We did 1 to 3 inclinations. So 1 for M87, since we know the inclination due to the jet. And for Sagittarius A star, we tried 10, 50, and 90 degrees, just to see the difference between face-on, edge-on, and intermediate case. There are 11 snapshots, just because there's a large dimensionality in the imaging already. We only did 11 to sample the time dimension. 4 different values of R high, if you're aware of this kind of temperature prescription that we use for the electrons. And we also worry about the electron distribution function. Usually these are assumed to be thermal, but especially for spectral index, non-thermal electrons matter very much. And so we also look at 3 non-thermal electron distribution functions. These are what we call kappa models that have a thermal core plus a power law tail and 1 free parameter determining the slope of that tail, this kappa of 3.55 or 7, which we use in our cases. So let's first take a look at some examples. This is the same exact GRMHD snapshot, ray traced in different ways. Different rows are M87 on top, then Sagittarius star face on, Sagittarius star edge on the bottom. The different columns correspond to different values of kappa, that is the amount of electrons that are in this high energy tail, where you've got more high energy electrons moving to the left. And one thing that you'll notice here is that, for example, if you focus on the top row, as you increase the fraction of electrons that are in this high energy component, the image becomes larger in extent, which is something that has been seen previously as well by Ferry Al-Ozel in 2000, Alwin Mao in 2017. And at the bottom of each of these panels, I've written a couple quantities. First, the spatially unresolved spectral index, which is all that we have access to at the moment, which I'm calling alpha net. And then the characteristic optical depth, intensity weighted across the image as well. You can see that this varies substantially with this particular snapshot, where we've got 0.01 on the top left and about 7 on the bottom right. Typically, the larger optical depths give you larger spectral indices, and you can see color-coded the spectral index in each individual pixel as well, showing that there's a substantial amount of variation that depends on the electron energy distribution. And this is only just one snapshot, and so there's a lot of options in terms of modeling these sources and what their spectral index maps will look like. This is doing the same exercise for a MAD. And you can see here that the differences are a lot less obvious. So the SANEs are more sensitive to the temperature and the electron distribution function than the MADs are, it turns out. So now let's take a look at all of these models. Here we're looking at the kappa of 5 ones. In this plot, I'm showing as a function of optical depth, the unresolved spectral index, where we thought initially that all we would find is just perhaps a 1-to-1 correlation between optical depth and the spectral index. But you can see that this is not the case. Many different dimensions are represented here. Different spins are different symbols, and you're not going to see a trend here. But you will see a trend between the closed symbols and the open symbols. That is MADs versus SANEs, where the MADs tend to have a much a more positive spectral index for a fixed optical depth than the SANEs do, telling you that optical depth is not the only thing that matters here. The SANEs
By the way,
actually,
maybe a minute or two before questions.
Okay,
if that's possible.
Sagittarius A star is not very different. Here we have these 3 different inclinations. It's slightly more positive, but that's about it. And it turns out that alpha of 0 is actually not the most natural value, especially if you believe that Sagittarius star is face on, as some people do from the infrared. So this can be potentially very constraining. Now, in terms of why the MADs have a more positive spectral index than the SANEs, We looked at two examples and are able to compute along each geodesic characteristic temperature, magnetic field strengths, and optical depths. And looking at this analytically, we find that these are really the three quantities that actually matter. So this is a MAD. Don't have time to go into most of these details, but this is the corresponding SANE. And if I were to flip back and forth between the two, the SANE has an alpha net of -1, the MAD -0.3. The main difference is the temperature, which varies by an order of magnitude. And there's this characteristic frequency for synchrotron that goes as the temperature squared times the magnetic field strength, which matters a lot for the spectral index. And so it is this which is driving the difference here. I'll skip over this and conclude saying that if we can resolve the spectral index, we expect that generically there's going to be a decrease with radius, as well as a spike in the photon ring, if that's actually resolvable. So here we've got the different models azimuthally and time averaged. And we've got the spectral index as a function of radius shown here, where the gray band is the photon ring. You see a spike there and a generic radial decline. The radial decline ought to be accessible even at 20 microarc second resolution. So here I've done the same thing as before, but just blurred with the appropriate kernel beforehand. And so in conclusion, models produce an enormous range of spectral index that we can use to discriminate models. Alpha net of 0 is actually somewhat high for Sag star for the GRMHD models that we looked at. MADs tend to have a more positive spectral index than SANEs. They're sensitive to the uncertain plasma heating parameters, not so much to spin. Generically, the spectral index ought to decline with radius already at EHT resolution. So this is something that we could potentially see very soon. And there's a clear spike in spectral index at the photon ring. This happens to be because geodesics probe stronger magnetic fields and higher optical depths. So thanks. I'm happy to take questions now.
All right, yeah, so we'll just give one question to Aditya because we have to move on soon. Go ahead.
It's a pretty basic question. So the conclusion says that it's insensitive to spin, but what about the black hole mass? Is it sensitive to, like, is it different for, say, stellar mass black holes and supermassive black holes? Thank you.
I'd have to think about that. It's so the main variables here are the temperature, magnetic field, and the optical depth. And so when it comes to scaling to different masses, one would need to scale those appropriately, and then also give it the right amount of flux, which means give it the right amount of accretion rate. So I don't know off the top of my head how this should evolve, but it's worth thinking about, especially if we want to look at more sources with ngEHT. And well, we have unresolved measurements for many sources, actually.
All right, so thanks a lot, Angelo. I want to give Cheyu time for his talk, but very good. Continue discussion in the chat and in the Slack that I put in the chat. Thank you.
Yes, can you see my screen and hear my voice?
Yep.
Okay, thank you. So let me start. So hello everyone, my name is Chen from the Institute of Physics, Academia Sinica in Taiwan. And the content of the talk is essentially based on these two papers. The first one was published in JCAP last year, and the other one is collaborated with Xiangyi Karen Yang from National Tsinghua University in Taiwan. And the paper is already on arXiv, and you can see the arXiv number over here. So basically what I'm going to talk about today can actually boil down to one simple question. What if the black holes in our universe do not have equatorial reflection symmetry? Namely, what if the black hole look different in its north and south hemispheres? So in particular, in this talk, I will mainly focus on the, due to this reflection, the symmetry, what happened to, for example, the accretion disk around the black hole, and also the ring image, the shadow image cast by this black hole. So at first you may think that the idea that black hole doesn't have Z2 symmetry is very crazy, but actually it is not. For example, if you consider like effective field theory, and essentially in effective field theory, we always include some higher order curvature invariance on top of the Einstein-Hilbert action, and you can see a very complicated action like this. In particular, if the theory contains some parity violating interactions, which, for example, it consists of some combination of Pontryagin scalar, then it has been shown by several authors in the literature that the rotating black hole spacetime in this theory generically do not have Z2 symmetry. The of Z2 asymmetry would also appear in some exotic compact objects made by, for example, ensemble of microstates, or for example, fastball models inspired in string. And usually this kind of asymmetry is induced by the spin of the black hole. So in this work, what I'm going to talk about is to study the phenomenology of this Z2 asymmetry. And why the way that we do this, what we want to do is that instead of considering some particular complicated model in a zoo, we essentially want to construct a theory agnostic metric spacetime, which contains a deviation parameter, controls this Z2 asymmetry. The spacetime looks very similar to curve, but different from it, and specifically designed to test this Z2 asymmetry. Okay, so this is what we want to do. And well, now we do have a metric, and I'm not going to talk about the detail how we construct the metric. The detail is all in the paper. And here I would just like to summarize what we have in the metric. First of all, the metric should reduce this to curve asymptotically as it should. And the second, the metric contains a single deviation parameter epsilon. And this epsilon controls the equatorial reflection asymmetry. So for example, if epsilon is 0, of course, the metric then reduces to curve. And the third, in this metric, we want to respect the existence of Carter constant, the existence of hidden symmetry, and such that it allows us to have a separable geodesic equations, which also simplify quite a lot the computations, okay? So one of the direct consequences of this Z2 asymmetry is that the accretion disk surrounding the black hole, in this case, is in general not a flat disk lying on a standard equatorial plane. Instead, in this case, it becomes a curved accretion disk, as you can see in this figure. And the reason for this is that it's very simple. So once if you consider the time-like circular orbits around the black hole, you will find that, okay, these orbits still exist in general, but they do not lie on the standard equatorial plane. Instead, they lie on some particular plane. Each orbit lie on a plane which is parallel to the standard equatorial plane, but different from the equatorial plane. So if you consider a collection of all these orbits, then you find that the accretion disk would have this kind of shape. And you can see that the accretion disk reduces to the standard equatorial plane when you go further away from the black hole. And this is nothing but due to the asymptotic flatness of the spacetime. But of course, this figure is a little bit exaggerated because we have zoomed in the Z direction scale in order for you to see more clearly this behavior. Okay, so in our work, we also try to understand what will happen to the ISCO, which is very important to understand the property of accretion disk, because ISCO usually defines the inner edge of the disk. And we find that essentially this deviation parameter epsilon, or the Z2 asymmetry, would generically shrink the size of the ISCO, okay? So you can see from this figure, this is a very busy figure, but you can focus on this black curve, which shows you a constant contour. And you can see that when we have a non-zero epsilon, you can see that this epsilon will essentially reduce the size of the ISCO radius, or in particular the prograde ISCO, okay? And this means that for a particle moving on the accretion disk, the particle is likely to move closer to the black hole. And this would also enhance the radiation efficiency of the particle during the accretion process. Okay, so we have this, we have already shown this explicitly in the paper. And the other important application, astrophysical application, is shadow, which is also related to the project of ngEHT. So this is the figure. This figure shows you the shadow critical curves in this curve-like metric. And there are two important remarks. The first one is that you can see from this figure, the contour, this critical curve of the shadow boundary is always symmetric with respect to the horizontal axis, no matter what the values of the spin or what values of the inclination angle are. And this is quite counterintuitive because remember, the space-time that we are considering here do not have refraction symmetry. But the contour, the critical curve, is always symmetric with respect to the horizontal axis. Okay.
So I just say 1 to 2 minutes until questions. So. Okay.
And the second interesting property is that this epsilon deviation parameter only changes the shadow size. It doesn't really change the shape. And this is very important in the sense that in terms of angular diameter measurements, there is no degeneracy between this deviation parameter epsilon and the spin or the inclination angle, because the later two always are more sensitive to the shape distortion. And well, I want to say one more word about the reason why the shadow contour, the critical curve, is symmetric with respect to the horizontal axis. Well, it turns out that this is highly related to the separability of the Joule equations. Namely, it is highly related to the existence of the Carter constant and also the existence of the hidden symmetry of the spacetime. So you can imagine that the hidden symmetry of the spacetime will manifest itself in the form of the symmetry, a vertical symmetry of the critical curve of the shadow boundary. And this is the future prospects of these projects. Well, the first one is maybe more astrophysics. Well, usually, you know, the usual accretion disk model is based on thin disk model for example, the Novikov and Thorne. But in this case, this kind of thin disk model is not reliable for this curved disk. So if you want to study the luminosity, temperature, or other more realistic astrophysical applications, we really need a reliable thin disk model for a curved disk. Okay, and this is still under construction. And the second extension is that, as I said, the critical curve is always symmetric with respect to the horizontal axis. And this is due to the hidden symmetry of the space-time, possibly. So the natural question is to see if to go beyond this critical curve, what if we consider the subring images of the ngEHT? Perhaps this Z2 asymmetry will manifest itself in some certain way that we don't know in these subring images. And I believe this will be a very interesting target to pursue in the future. Okay, so that's it.
Thank you. Thank you. Very nice, Chiwe. So I will let a question come here if there is one, and then we'll move the question to the chat after a question here. Does anyone have a question immediately for? All right, if no one has a question, I just want to know how some of these Z2 deviations from symmetry compare to the natural triaxialities and some of the potentials that we're seeing. So we already know that there's, the symmetry is broken in nature because of the local environment. So how does some of the other astrophysical uncertainties compare to the amount of deviation you see in these theories?
So basically first of all, I would like to answer this question by saying that this model is actually considering an isolated black hole. We do not have the Z2 symmetry induced maybe due to some fundamental reasons, like in the effective field theory, quantum gravity effects, for example. And of course, it can also be due to some astrophysical environment, as you said. And I'm not very familiar with the triaxial property, but perhaps there could be some difference between these two scenarios. But yeah, I would say in this case, this Z2 asymmetry is likely to be due to some fundamental physics.
Thank you. Thank you. So let's get the rest of the questions to the chat in the Slack, and I will give the.
Can you all hear me?
Yep. And we see your the panels of this. Yeah, now it's good.
It's okay now? Okay.
Yep.
Okay. So hi everyone. My name is Koushik Chatterjee. I'm a postdoctoral fellow at the Black Hole Initiative at Harvard University, and today I kind of wanted to show some of my work in imaging warped and bent jets especially when you have when you remove some of the assumptions we take, especially in ngEHT modeling. So moving forward, most of the simulations or theoretical models that we usually encounter in the MHD world, let's say, kind of have a structure similar to this, where you have a black hole rotating along, let's say, the z-axis, and the disk resting on the mid plane, and then the jets are sort of traveling both up and down along the black hole spin. Beginning with Fragile et al. 2007, there was this starting of the exploration where what happened when the disk and the black hole spin axis were misaligned. So what kind of geometry flows you produce, and overall what kind of images. So one important parameter in this respect is this tau parameter, which denotes the angle between the black hole spin vector and the jet axis. Now why I mentioned this will become more it will be more understood in the later talks. But overall, over the following recent few years, there has been much work going into this, especially look into how such models can affect, let's say, our understanding of the ngEHT image of M87, for example. So just to show you all how the disk and the jet looks like in such a model. So here we have a black hole which is spinning around the z-axis, but the initial disk was is tilted at an angle of 30 degrees. And on the left, I have is a gas density within the inner 50 gravitational radii, and on the right is a zoom out of that. And when I play it, you see what happens that at larger radii, at larger radii, the jet and the disk are aligned with one another. That is, the jet is basically perpendicular to the disk. But at smaller radii, both the jet as well as the disk sort of warp around or tend to align with the black hole spin axis. This is where the tau parameter sort of comes in. So the plot on the right shows this tau parameter with respect to radius for both the disk as well as the jet. Now, if both of these quantities were 0, then we would have perfect alignment of the disk as well as the jet with the black hole spin axis. And what you see is that overall, if you, let's say, start with an initial disk with a tilt angle of 30 degrees, that over time, the inner part of the disk does align, but not so much, but the outer part stays misaligned. And so we have a change in orientation at tens of gravitational radii. And what you can do is you can do the same experiment, but placing the disk at a larger tilt angle, for example, at 60 degrees. And you see that the change in orientation is much larger, so it's much more drastic. Now, another interesting thing that happens when you have such a model is that the inner part of the disk stresses, which I think James Miller Jones sort of talked about in his presentation earlier today. And what you're left with is that the inner disk has precessed away while the outer disk doesn't precess as much, and so you have a warp in the disk as well as in the jet, which you can actually see in ngEHT scale images. And this is exactly what we try to do over here. So this is the actual ngEHT image that we took in April 2017, and on the right are reconstructions, either using the ngEHT 2017 array or the new ngEHT array that we're sort of looking into which array configuration would be the best. And credit goes to Alex Raymond and Daniel Palumbo for sort of coming up with these scripts with which I was kind of able to do these reconstructions. So as we go from top to bottom, what we're doing is we are increasing the tilt angle of the disk. So going from a normal aligned this model up to 30 degrees initial tilt to 60 degrees initial tilt. And what you see is that in the ngEHT images, at least in the log scale, the images look pretty similar, but not too similar. But more or less, all of them show this southern bright crescent, but the extended emission is not at all constrained, which we are actually able to see far better with the ngEHT configuration. So this is where the dynamical range in flux of ngEHT would be very much useful. One other thing is that we have the extended flux, but we also have the shadow size, which you will be able to better constrain with the ngEHT. And you do see that the shadow size changes as you change your tilt angle. So this is just one of the applications with ngEHT. Now, another important aspect of this problem is what happens when you change the magnetic field strength near the event horizon. So for example, if you start with a weak magnetic field or a sane magnetic field and then increase up to a mad magnetic field, how does this tilt parameter change? Because this actually shows us the jet and the disk orientation, right? So for a weak field or the sane disk model, you see that the disk remains very much misaligned even at very small radii. The black holes is actually unable to force the disk into alignment in this case. Now, as you increase this magnetic field, you see stronger alignment towards the black hole spin axis. And finally, when the magnetic fields become dynamically important, that is when you have, for example, a magnetically arrested disk scenario, the usual profile that we saw from the weaker field scenarios go away, and you have a disk which is more or less aligned within the first few gravitational radii, and then sort of warps away at a few tens of gravitational radii, but in the other direction. So these are just fish out of the oven. Images for mad aligned, strong field misaligned, and mad misaligned. So strong field misaligned means you're not quite mad, but you're still strongly magnetized. So sort of like what you would expect, maybe applicable in the M87 scenario. But what you see, like just from a quick look, is that the mad field, both in the aligned and the misaligned case, looks very similar, while in the strong field case, it does not. And this is because the tilt angle or this tau parameter is very different. And this is where the dynamical range in flux will become very important, as well as capturing these systems at a high enough cadence to see whether there are small scale events that take place. Because in misaligned systems, usually the variability in flux is higher, as well as you see small scale shocks and reconnection events often occurring. And of course, because I'm a theorist, why limit myself to just 60 degrees aligned disk? Let's do the extremal case, which is the 90 degrees aligned disk. So over here as well, the black hole spin is pointing in this positive z direction. Richard, how am I doing on time?
Oh, just a minute until questions. If you
awesome. Yeah, this is my second last slide, so all good. Right. So and then you have the this sort of spinning in the negative x direction. And what happens in this case? Why isn't is that you do have accretion, you do have some transient effects going on around, but and since this the initial field was said to be that of what you would typically expect a magnetically arrested disk to be, you do still form a jet. The inner part of the disk is sort of forced to be aligned. The jet actually forces the disk to align itself quite a bit, but again, there's a lot of precession going on. There are some transient outbursts that you will see sometimes, and as well as the jet is often twisted. However, eventually, once you run the simulation long enough, the jet still forms when the disk sort of has attained an equilibrium state. For example, that's an outburst right there. But yeah, so the important thing is that with these sort of initial conditions or initial disk configuration, connections to other types of accretion flows, such as boundary-like flows, would be very important, just because the jet disk or jet accretion flow interaction would be very, very interesting in those systems. And so just to summarize, warping of the disk and inner jets influences the shadow region quite a lot. It influences the how the ngEHT scale image looks and how the extended region looks like. And so ngEHT would help with a lot in that. Additionally, in addition to the jet disk morphology, there's a lot of sources of variability in this system, such as you can have shocks because the disk is forced into this into a different configuration. You can have pinches, you can have kinks because of the interaction of the jet with the disk or with any sort of inflowing material. And you can also have this discrete ejector that also I think James mentioned quite a bit because of these transient jetted features which travel outwards. And this is where sort of ngEHT comes in because it can actually connect the horizon scale image to the jet launching area and beyond. You can test tilted disks and also test this inflow outflow variability. That is actually very important when you are thinking about how does power in the accretion flow travel onto the jet. And I think I'll leave it at that.
All right, thanks, Koushik, for the tilted disk work. And we are just 3 minutes over right now, so I will let one question come. If anyone here has a question, maybe we can ask a quick question before the break, and maybe you can type the rest of them in the chat. Or no questions from anyone?
If I may, can I ask a quick one?
Yeah, go ahead.
So the quick question is, do you put, what kind of ambient pressure profile do you put your jets in when you are simulating all these cases?
So just because we wanted to see only the jet disk interaction, our ambient medium is negligible. But of course, you can also have like a smaller disk and then have a more dense ambient medium, which the jet rams into, and then you can have all of these kinked features. Okay, we are doing that, but in a separate project.
Okay, thank you.
All right. Well, I think that we had a very full and interesting and varied session today. So I'm going to let everyone either continue on in the chat or go back to the main room. And yeah, thanks for the speakers and thanks for listening.
Thank you, Richard.
Of course.